Hello, my dear friends. I am Shubham from Learnohub, the free learning platform where you can study physics, chemistry, maths, biology absolutely for free at learnohub.com. So then, let's start. So students, in this video, we are going to start with your new chapter of ICSE Class 9 Chemistry, which is study of gas laws. Okay, this is chapter number 7. Yeah, you all know. And we have completed so far the 6 chapters of your Class 9 ICSE. Now, in this video, we are going to start with the concepts of this chapter. In between, we will also solve some numerical problems. Okay, the questions. So, without wasting much time, let's start and let's rock. Okay, now students, as the name of this chapter suggests, which is study of gas laws, so exactly we are going to study the gas laws. Okay, now which gas laws we are going to study? Boyle's law and Charles' law. So let's first start with the Boyle's law. Okay, now what is Boyle's law? Simply, I have already told you. Okay, whenever we see a law which is named after a scientist, it means that the scientist has given that law. Fine. Now here Boyle has given this law. Okay. Now, what is the law, okay, or what Boyle stated as his law is simply what he observed through his experimentation. Very simple. Now, once we start to understand what he observed through his experimentation, we actually directly, okay, we indirectly understand the law given by that particular scientist. So, let's try to understand what actually Boyle understood from his experiments. So, he carried out the experiment in his in the J tube. Okay, now we are not going to go into the details of the experiment, but what he concluded from this experimentation, that we are going to see, okay, which will help us to understand this law. And the thing is very easy. Okay, very simple observation. So when he was experimenting, we need to understand first two things which he kept constant. First is he was experimenting with the gas. Fine, we are talking about the gas laws. So here Boyle was experimenting with the gas. Okay, so what he did, he kept the temperature of the gas constant. Okay, temperature of the gas constant, as well as the amount of the gas, whatever amount of gas he took throughout his experimentation, he also kept the amount of the gas fixed. Okay, so I can write the amount of the gas is also constant. Fine. Now, by keeping these two things constant, what he observed, when the volume of the gas, okay, was seen to be decreasing, was observed to be decreasing, the pressure exerted by the gas was observed to be increasing. Okay, so when the volume of the gas is observed to be decreasing, the pressure exerted by the gas was increasing. Okay, so this observation he could make through his experiments. Okay, he took the values of the volume as well as the values of the pressure. Okay, values of the volume of the gas and values of the pressure exerted by the gas. And by looking at these values, he figured out that, oh, when the volume of the gas is decreasing, the pressure exerted by the gas is increasing. Fine. And he simply stated this observation in the form of his law, which is called as Boyle's law. So what is Boyle's law? At constant temperature, see, the temperature is constant. Okay, whatever he has observed now, that only he has stated in the form of the law in whatever English he likes to write. Okay, so yeah, I'm joking. So at constant temperature, the pressure of a fixed amount of gas. So here, fixed amount of gas. So both the things he stated in his law. Now he's talking about the pressure. So what about the pressure of the fixed amount of gas? The pressure is varying inversely with its volume. Okay, now this term, pressure is varying inversely with its volume. And whose pressure? Pressure of the gas. Okay, so first of all, the two things which are kept constant we have seen. At constant temperature, okay, the pressure of fixed amount of gas. So fixed amount of gas, right? So both the things he stated. Then he's stating that the pressure of this fixed amount of gas is varying inversely with its volume. So this means that what is this inverse variation? Inverse variation means the opposite variation. You can understand in this way. Okay, if one thing is increasing, the another thing would be decreasing. Okay, now here also same is happening when the pressure is increasing. Okay, or suppose if the volume of the gas is decreasing here, so the pressure is observed to be increasing. Pressure exerted by the gas is observed to be increasing. It is not decreasing, same like that of the volume. So if we are seeing the opposite effect, okay, or opposite variation, we say that they are inversely proportional. Fine. So here we can say that volume and pressure are inversely proportional, because if one term is showing a particular increasing effect or decreasing effect, the another term would show the opposite effect. Okay, if now here volume of the gas is observed to be decreasing, the pressure exerted by the gas is observed to be increasing. So that's why we say that they are inversely proportional to each other. Clear? Fine. Now this thing only he stated. So pressure of the gas varies inversely with its volume. Correct? Because here when volume of the gas is observed to be decreasing, the pressure exerted by the gas is observed to be increasing. Fine. So since both of them are showing the opposite effects, okay, or opposite trend, one is showing the decreasing trend, another is showing increasing trend. Okay, so that's why they are said to be inversely proportional to each other, and that's what is stated in the law. Okay, so how we can write this? Okay, this inverse proportionality between this volume and pressure, how we can write this? Okay, now by using the proportionality symbol. Okay, so I can write in this way: volume is, okay, proportional. Now here I am writing the proportionality sign, but now proportionality, after that I am writing 1 by P. Okay, so this means that volume is inversely proportional to pressure. Okay, when I am writing, okay, when I am saying inversely proportional, okay, if one term I am saying it is inversely proportional, okay, to the another term, I must make sure that the another term must be written as the inverse. Okay, so pressure should be written as the inverse of pressure. Inverse of pressure means, okay, simply 1 by P. Okay, if pressure is P, right? I am denoting pressure by P. So inverse of pressure would be 1 by P. Okay, so if I am saying that volume and pressure are inversely proportional, so if I am writing volume as V, then I am writing the proportionality sign, and then I have to then if I want to show here that they are inversely proportional, then I have to inverse the another term. So that's what I have done. Fine. So how we read this as volume is inversely proportional to pressure. Okay, fine, clear with this point? So now if I want to make it more simple, if I want to remove this proportionality sign, okay, so how I can do this thing? Okay, I can just write simply volume. Okay, for removing the proportionality sign and putting is equal to sign, we need to add a constant, okay, term. So I'm denoting that constant term with K. Okay, so volume, removing the proportionality sign by is equal to, okay, need to add a constant on the side of 1 by P. Okay, so I'm adding constant K on the side of 1 by P. Okay, fine. So this thing, oh, 1 minute. So see, the proportionality symbol, I have replaced it by this. Fine, is equals to constant. So volume is inversely proportional to 1 by P, or I can say volume is equals to constant 1 by P. Clear? Okay, fine. Now I can write this as in this way also. Okay, PV, right? I can put here P. PV is equals to K. Okay, PV is equals to K. Now further we are going to see how we can more simplify this equation, okay, so that we could solve some problems. But for now, let's stop to this equation and let's try to understand why, when we are decreasing the pressure, when we are decreasing the volume of the gas, the pressure exerted by the gas is increasing. Okay, in short, let's try to understand why Boyle has observed this thing, or why do we observe this thing when we experiment just the same way like the Boyle did. Okay, so the explanation, okay, of the Boyle's law we are going to understand in the terms of molecular motion, or the motion exhibited by the particles. Okay, so I can say it as particular motion as well. Okay, simply the motion shown by the particles. Okay, in that terms we are going to understand the Boyle's law, simply the inverse proportionality of pressure and volume. So now I am having a container. Okay, I have fixed this, okay, lid. Now this lid is adjustable lid, sir. You can say in this way. It is called as piston. So this piston, okay, I am having a support over this piston in order to move this piston up and down, okay, in this container. Now what I have done is I have taken a fixed amount of gas here. Okay, so first thing, amount of gas is fixed. So amount constant, fine. Also, what I'm going to do is I'm going to keep the temperature of the gas constant. Okay, so temperature also constant. So temperature and amount constant. Clear? Now what I'm going to do is I'm going to, let's check what is happening, right? So I'm going to reduce the volume of the gas, volume occupied by the gas. Now initially this much volume is occupied, fine. Now let me tell you what is pressure actually, right? So here pressure means the force exerted, okay, by the gas here. Okay, if you're talking about the pressure exerted by the gas, this means that the force exerted by the gas, okay, on a particular unit area. Now on whom we are saying about the pressure is exerted by the gas on the walls of the container, fine. These are the walls of the container, okay, yeah. So the pressure exerted by the walls of the container, how can I say it in simple terms? It's simply, what it means, that it's simply the force exerted by the gas particles, okay, on a particular unit area of the wall of the container. So if I'm considering this unit area, okay, suppose this is a 10 meter, okay, height container. So out of this is 1 meter, for example, this is 1 meter, or I'm saying this is a 5 meter height container. So out of this is 1 meter. Okay, now I'm taking this as a unit area. 1 meter means, unit means 1, right? So unit area means 1 meter, 1 meter square area. Okay, I'm supposing this, fine. Now in this 1 meter, or in this unit area which I'm talking about, here the number of molecules which means the gas molecules, okay, or the number of gas particles which are hitting this unit area of the container, okay, at this particular point of time, you can see when the volume is this much, is not too high. The number of molecules which are hitting to this unit area, okay, of the container are not too high. Okay, so if there are not too many molecules hitting on this unit area, this means that the pressure is not too high. Okay, or suppose like the pressure is something equals to X, for example. Okay, or let's take it as a number which would be easy to understand. Suppose 100. We are taking as an arbitrary number of the pressure as 100. Okay, now when I would decrease the volume of the gas, you can observe the number of molecules hitting to this unit area of the container would increase in a particular time interval. Okay, so if I'm talking about 2-second time interval, so now initially the number of molecules you can observe are not too much hitting to this unit area of the container in 2 seconds or in 1 second. Okay, but now when the volume of the gas would be reduced by keeping these two things constant, the temperature of the gas and the amount of gas, you would observe that the number of molecules hitting to this unit area of the container, okay, in a 1 second would be more. So if the number of molecules are more, then the pressure exerted is more. Fine. If number of molecules or number of particles are more, then this means that the pressure exerted by the gas particles is more. Fine. Now initially see, there are not more number of particles hitting to this unit area in 1 second. But now you would observe, I am now reducing the volume. See? Okay, slowly and gradually, you can observe here, the number of particles hitting to this unit area in a second, it is increasing, right? Right? See. Correct? Wait a minute. I will show you again. See. Okay. Just observe to this unit area, the number of molecules hitting with the decreasing volume. When the volume is decreasing more and more and more and more, the number of molecules hitting this unit area are increasing. Correct? So if the number of molecules hitting that particular unit area is increasing, this means that the pressure is increasing. When volume is decreasing. When volume is decreasing. So we reach the same thing. When volume is decreasing, pressure exerted by the gas is increasing. When the volume of the gas is decreasing, pressure exerted by the gas is increasing. Okay. So we could understand this thing in terms of the motion of the particles. Okay. Clear? Now see, in this context, okay, you need to understand that whenever we are keeping the temperature of the gas and the amount of the gas constant, okay, a very important thing is, here you can see that you would say, sir, if we are decreasing the volume, okay, if the speed of the molecules of the gas particles which are here, means if the speed with which the gas particles are moving, if that also gets reduced, then the number of molecules hitting this unit area would get reduced, right? So why the speed of the gas molecule is not reducing, though we are decreasing the volume? This is because whenever we keep the temperature and the amount of the gas fixed, the average kinetic energy possessed by the gas particles or the gas molecules, it also remains constant. This means that in simple terms, the speed of the gas particles with which they are moving, that would remain constant. Okay, so if the speed with which they are moving, that would remain constant, then obviously if we are giving them less space, they would hit more frequently the particular unit area of the container. And if they would hit more frequently, this means that the more and more number of molecules are hitting that particular unit area of the container in that particular time interval, for suppose 1 second. So if more and more number of molecules are hitting, then the pressure exerted on that unit area is increasing, correct? When the volume is decreasing. Clear? Got the point? Okay, so this is all about the explanation of the Boyle's law in terms of molecular motion or particular motion or the motion of particles. Now, let's represent let's try to understand with the help of the graph, okay, or let's just represent the Boyle's law in the terms of graph, okay. So, if suppose we are carrying out the experiment just like the Boyle, okay, and we have experimented by keeping the two conditions same, just like how Sir Boyle did, okay. So, by keeping those two conditions same, that is the temperature of the gas and the amount of gas, okay, we could observe that the pressure of the gas, okay, the pressure exerted by the gas would be inversely proportional to the volume of the gas, correct? So we would have some values of the pressure exerted by the gas, tick, 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 for example, and we would have some values of the volume, okay, of the gas. But now here we are going to plot, okay, the not the pressure against the volume, okay, or not the pressure and the volume, these two things. We are going to plot pressure and 1 by volume. Why? Because we have seen that, see, pressure, okay, is inversely proportional to volume. We are saying in this way. So this means that, see, if we would say in terms of directly proportionality, okay, direct proportionality, this means that pressure is directly proportional to 1 by volume. Okay, see, there is a difference. Pressure is, by looking at this thing, we can deduce that pressure is inversely proportional to volume, okay, just the volume V. But if I want to write this if I want to say it in terms of directly proportionality, okay, direct proportionality, so I can say that pressure is directly proportional, okay, to 1 by volume, okay, the inverse of the volume. Fine. So simply, if you want to convert from the inverse proportionality to direct proportionality, you have to change the another term to its inverse. Clear? Fine. So this is the main thing which we need to understand, or which we could easily just figure out by looking at this graph. See, because here pressure is directly proportional to 1 by volume, okay, the inverse of the volume. So that's the reason when we are observing in this gas for a particular temperature, suppose T1, suppose if this is 25 degrees Celsius, okay, suppose. So at this particular temperature, okay, if we could observe pressure, now I am saying that pressure is directly proportional to 1 by volume. This means that when pressure is increasing, volume 1 by volume would also be increasing, not volume, 1 by volume would be also increasing. If pressure is decreasing, okay, fine, so then 1 by volume term would also be decreasing. Okay, so you can observe here, okay, see, this is what is Boyle's law, pressure inversely proportional to volume, okay, we can read it in this way. If we want to read it in the terms of direct proportionality, so we can read it in this way, that pressure is directly proportional to 1 by volume. In other words, we have actually written this thing only, okay, we have written pressure directly proportional to 1 by volume. This is actually pressure directly proportional to 1 by volume, okay. But if we want to say it in terms of just volume, then we say that pressure is inversely proportional to volume. Clear? Fine, don't get confused in this thing. It's quite simple. So as we have seen when we were seeing the statement and the Boyle's law. So at that time I have deduced this thing. I have explained you this thing, that pressure is inversely proportional to just volume, Okay, or in other words, if you want to read this thing in terms of direct proportionality, so we can say that pressure is directly proportional to 1 by volume. Clear? Fine. Now here, this means that if pressure is increasing, 1 by volume would also increase, or if pressure is decreasing, 1 by volume would also decrease. So see here the pressure is increasing. Okay, see, pressure is increasing, right? Means this means that, see, pressure is increasing, na? At this point the pressure is this much, at this point, okay, the pressure is this much. Fine. So as we are increasing the pressure, okay, or as we are observing the increase in the pressure, okay, the volume is also increasing. See, right? Correct? Oh, sorry, 1 by volume is also increasing. So when we are seeing and observing an increase in the pressure, okay, from 0 to this point, then we are observing increase in the 1 by volume also from 0 to this point. Correct? If you are observing more increase in the pressure from this point to this point, okay, then we are observing further increase in the volume from this point to this point, right? So as the pressure is increasing, 1 by volume is also increasing. Correct? Pressure is increasing, 1 by volume is also increasing. Clear? Now, in another words, okay, if I want to write that the pressure is directly proportional to volume, I would write in this way. Okay, pressure, simply proportionality sign and volume. But if I want to write pressure is inversely proportional to volume, then I have to write pressure, same this proportionality sign, and since I want to write it as inversely proportional to volume, so I would write inverse of the volume. Clear? Now in case of Boyle's law, this is not the case. Okay, pressure is not directly proportional to volume. Pressure is inversely proportional to volume. So I have written in this way. Fine. So this is the way which we have studied earlier. Okay, pressure is inversely proportional to volume. Okay, but if I want to read it in terms of direct proportionality, then I would read as pressure is directly proportional to 1 by volume. Clear? Fine. Okay, now moving ahead. So this was the graph which showed the direct proportionality between pressure and 1 by volume. See, pressure and 1 by volume, direct proportionality. Okay, it's up to us that how we want to read this as. Okay, if we want to read it in terms of direct proportionality, this equation, okay, or this equation, both of them are same. So I can read it as pressure directly proportional to 1 by volume, or pressure inversely proportional to just volume. Okay, so this was the graph which was telling us that both the things are actually the same. Pressure is directly proportional to 1 by volume, okay, and pressure is inversely proportional to volume. Both the things, okay, would result into the same thing. But here we have observed the direct proportionality between pressure and 1 by volume. Fine? Means I mean to say that pressure is directly proportional to 1 by volume, or pressure is inversely proportional to volume, just volume. Both the things are actually, okay, telling us the exact same thing, that pressure and volume are inversely proportional. Fine? But here we have seen pressure and 1 by volumes direct proportionality. Okay? Pressure and 1 by volumes direct proportionality. Clear? Now in the next graph we would see the pressure and volumes inverse proportionality. Okay, how? See here. Now inverse proportionality means I can just write pressure proportionality sign 1 by volume. Okay, so I would read it as pressure is inversely proportional to volume. Fine? Inversely proportional to volume. Fine. This means that when pressure is increasing, volume is decreasing. Clear? Now you can observe in this graph the same data. Okay, now here, now not the same data, but if we are having another set of data of the pressure and the volume, okay, pressure exerted by the gas and the volume of the gas, okay, we have carried out the experiment again. Okay, now suppose for example at this 400 Kelvin, okay, for example, now this 400 Kelvin is simply the temperature. Okay, now here the unit is not degree Celsius, it is Kelvin, but we are going to study about that unit. But for now, in Boyle's law, since the temperature is constant, we are not bothered about the temperature thing as such. Okay, so for now you just understand it in this way, that at a particular temperature which is kept as constant temperature. Okay, now at this constant temperature, okay, we are having the data of pressure exerted by the gas and the volume of the gas. Okay, so we have plotted the data, okay, on this graph, okay, of pressure and volume. Fine? Means the graph, okay, showing pressure of the gas, pressure exerted by the gas and the volume of the gas. Now, after plotting the points, okay, after plotting the values of pressure and volume, what we could observe is that, see, when the pressure, okay, or suppose if the volume, okay, is decreasing, here, suppose the volume is 100, okay, for example. Now, since it is decreasing, right, it is decreasing, we are going in this way, okay, see the curve in this manner, okay, so volume is decreasing, right. At this point, the volume is decreasing, more decreasing, right? So when the volume is decreasing, fine. When the volume is decreasing, what would happen? According to the Boyle's law, since pressure is inversely proportional, pressure would be increasing. The pressure exerted by the gas would be increasing, and you can see here the pressure is at this point it is this much, at this point it is this much. Increasing. Okay, so since we have observed now volume is decreasing, okay, in the same manner pressure is increasing, correct. At this point volume is this much, pressure is this much, fine. But at this point volume is this much, fine. This is less, but pressure has increased. Volume has decreased, but pressure has increased, correct. Fine. I would show it in another. See, volume is decreasing, okay, from this point to this point, okay, but at this point the pressure is this much, fine. At this point the volume of, at this point, okay, the pressure is this much. At this point the pressure is this much, fine. So when the volume was 100, suppose, okay, pressure is this much, okay, for example 12. Now when the volume is 50, the pressure has increased, it has become 24, fine. Okay, so in this term, so see, when the volume is reduced or when the volume is decreasing from 100 to 50, okay, the pressure, okay, at 100 it is 12, but then at 50 it is 24, okay, so pressure is increasing, volume decreasing, pressure increasing, fine. This is the simple thing which you can observe through this graph. So this graph is telling us the inverse proportionality between pressure and volume directly, okay, pressure and volume, okay. So the equation is exactly the same thing, the denotion of the law is exactly in the same way, but here we are seeing in the graph the inverse proportionality between pressure and volume, okay. In the previous one we were observing direct proportionality between pressure and 1 by volume, fine, okay, clear. So now in order to solve the problems, okay, we need to understand one very important thing which Boyle could conclude, okay, by looking at these graphs or by looking at the data. Now you can see here, okay, when the volume was like 100, for example, suppose liters, okay, we were taking as liters, or suppose ml, okay, volume as 100 ml, or just forget about the units, okay. So here volume is 100, okay, the pressure is 12. So if I would take the product of pressure and volume, okay, I am considering this 100 volume as volume 1, okay, initial volume of the gas, and the pressure 12 as the initial pressure, okay. So I am denoting it with 1 1. So P1 V1. So initial volume is V1, which is 100 of the gas. Initial pressure is P1, which is 12, okay, of the gas. Means pressure exerted by the gas is P1, okay, an initial one. So initially the pressure exerted by the gas is P1, which is 12. Now I am writing the product. The product is 1200, okay, of pressure and volume, okay, initially. But now the same gas, what we did is we reduced its volume to 50. Clear? Now here, after reducing the volume to 50, now this is the volume after the reduction of, means this is the volume when after reducing the volume of the gas. So we are taking it as V2, but the gas is same, okay, the gas is same, okay, also the amount is same, okay, amount of gas is also same, and we have kept the temperature also same, right? Because this data, okay, when we are seeing this, when we are looking at this data, okay, we know that the temperature is kept constant. We are talking about the gas, okay, which is whose amount has not been varied. So we have taken the fixed amount of gas. So this data is of, okay, or this data is collected by keeping the temperature of the gas constant and the amount of the gas also constant, okay, by taking the fixed amount of gas. So both these things are constant, okay. Now initially the volume of the gas was 100, pressure was 12, so I have taken the product of pressure and volume of the fixed amount of gas at the same temperature. Clear? Now later what I did is I reduced the volume of the gas to 50, so V2 becomes 50, okay. But now at this volume the pressure exerted by the gas is 24, okay. So pressure exerted by the gas is 24. Now see, I'm talking about the same amount of gas at the same temperature. Fine, clear? So by taking the same amount of, by keeping the amount of gas fixed and by keeping the temperature fixed, when I'm decreasing the volume to 50, the pressure is increasing to 24. So V2 is 50, P2 is 24. Now if again I took the product of this P2 and V2, okay, I would simply get, see, 24 5s are, if your math is like quite strong, so 25 is 100, right? 4 5 are 20, okay, so 120, 120, and this 10, which means 1200. Clear? So now in this graph, wherever you can point, means plot the point, okay, you can observe that at whichever volume you take, means whichever volume value you take, corresponding pressure value you take, okay, you take the product of the pressure and volume, you would always get this 1200 answer, okay, as the answer. So this means that the product of pressure and the volume, okay, of the fixed amount of gas at constant temperature is constant, correct? So I would just write it in this way, okay, product of pressure and volume, okay, of fixed amount of gas, okay, amount is fixed at fixed temperature of the gas. So this means that these two things are constant, okay. So see, the product of pressure and volume of fixed amount of gas at fixed temperature of the gas, okay, okay, is constant, 1200 1200. Now you just go back and see. Now let's go back and see what we have deduced, the mathematical form, okay. We have deduced till this point pressure and volume in when we are taking the product, it is equals to the constant, correct? So the same thing we have seen here, correct? By experimentation only Boyle deduced to this point. So this means that for a fixed amount of gas, when the temperature of the gas is kept constant, okay, whenever, okay, you take the product of its pressure and volume, okay, though the volume and the pressures be different, okay, at any particular point of time, but their product will always be equal to a constant value, okay. So in terms, by simplifying this thing, we can say that, see, P1 V1 is equals to 1200, correct? Fine. P2 V2 is also equals to 1200. So let's simplify this thing. PV is equals to constant term, okay. So this means that P1 V1 is equals to P2 V2, correct? Correct, since both of them are equal to a constant value, and since both of them would always be equal to a constant value, okay, both of them would be equal to each other. So that's the thing we can write here, that P1 V1 is equals to P2 V2, and this thing we can use to solve the problems, okay. So we need to use our brain, not just the formula. How the formula came, okay, or why we are using this formula? Because when we are keeping the temperature of the gas constant and we are taking the fixed amount of gas, then we are observing that whatever be the pressure and the volume values of the gas, whenever we get the multiplied product of both the pressure and the volume of the gases, okay, at whatever values, okay, of volume or pressure, by keeping these two things constant, okay, we get the product of the pressure and the volume of the gas as the same constant value, Okay, so if at this point we are considering the volume and the pressure, okay, if some at another point we are considering the volume and pressure, if some at another point we are considering the volume and pressure, okay, or now this point we are considering the volume and pressure, okay, we are going to get the product of pressure and the volume is equal to the constant value. Okay, product of pressure and the volume is equal to the constant value, provided we are keeping the temperature of the gas and the amount of gas constant. Clear? So this thing we observed, okay, by simply calculating with the help of, okay, a raw data, a rough data, okay, and then we could reach this equation, P1 V1 is equals to P2 V2. Fine. So in the problems as well, we need to use our brain and then we need to apply the formula. Clear? Now before going to solve the problems, let's quickly go through the units of pressure and volume, because that would help us in solving the problems, okay, and solving the questions. Now unit, starting from the pressure, the SI unit is Pascal, okay, or Newton per meter square. Clear? Now in case of some another units, if they are given in the question, so what another units you need to know is some another units of pressure are atmosphere or mm of Hg, okay, millimeters of Hg, or torr or bar. Okay, now let's have a simple correlation between, okay, some of the units, that is 1 atmosphere, which means how many mm of Hg, okay, or how many torr. Okay, so 1 atmosphere means 760 mm of Hg. Okay, 1 atmosphere is equals to 760 mm of Hg or 760 torr. Fine. In the same way, 1 bar, okay, we are going to see the correlation of 1 bar in terms of pascals. Okay, so 1 bar simply means 1 lakh pascals. Okay, so these are the simple conversions which you should know, okay, for the sake of solving the questions, because if they would ask you the pressure in torr, okay, if they are giving you the pressure in atmosphere unit and they are asking you the answer in the pressure, answer of the means answer, okay, in units torr, okay, then you need to know the conversion, right? If they are giving you the pressure in terms of bar and they are asking you in answer, you should denote the pressure in terms of Pascal. So then you should know the conversion. That's the reason you need to, means just remember this thing, a simple factual thing, okay, nothing more than that. And then volumes, SI unit is cubic meter. Okay, so most of you may not be knowing this thing, okay, no issues, because we don't actually use this cubic meter, okay, unit. Why? Because it is way beyond too much for us to use at a small scale level or at the lab level. Okay, why? Because we are considering at the lab level small amounts of chemicals, okay, or small amounts of substances. So that's why we don't use meter cube unit. Now why I'm saying this, because normally we tend to use this unit, ml, liter, okay, milliliters and liters. Okay, so simply you need to remember, okay, cm cube is same as the ml. Okay, so whenever you are seeing the volume in units cm cube, for example, suppose if I'm taking, I have buyed 500 cm cube of milk, this means that I have simply buyed 500 ml of milk. Okay, or if I'm saying that dm cube, if I have buyed 1 dm cube of milk, this means that I have buyed 1 liter of milk. Okay, because dm cube is exactly the same as that of the liter. Okay, some another means you can just say that they are, you can just remember in this way, dm cube is same as liter. Fine. Now it's very simple correlation. How many milliliters means 1 liter is how many milliliters? Correct? 1 liter is how many milliliter? It's simple, 1000. Perfect. Okay, so in the same way you can just write, now you can tell me 1 dm cube is how many cm cube. Now just apply your brain, just now we have seen the thing. Okay, so you can pause the video and just you can convert. It's quite simple. It would take hardly 2 seconds. Okay, so I hope you would have answered it correctly. Okay, because we know liter is same as the dm cube and ml is same as the cm cube. So 1000 would be the same thing, right? So 1 liter means 1 dm cube. 1000 ml means ml is same as the cm cube, right? So 1000 cm cube. Simple, correct? So 1 liter means 1 dm cube. Okay, ml means cm cube. Okay, so I'm writing, just replacing ml by cm cube. So 1000 I would write it in the same way. So 1 dm cube is equal to 1000 cm cube. Okay, but now why don't we use this meter cube unit? The answer is very simple. Okay, if you would try to convert, okay, if I'm asking you this question, okay, try to solve it. Okay, I hope you could do this if you would know the decimeter, meter, what means how many decimeter is 1 meter and all those things. Okay, you can figure out how many, or 1 meter cube is how many liters. Okay, so I hope you would try it on your own. Okay, it's quite simple. You just need to convert. I would just simply tell you the answer. 1 meter cube is equals to 1000 liters. Now you would be able to figure out that why we don't use meter cube as the unit, because it's too much, right? If I'm saying that I'm taking 1 meter cube of chemical, which means that I have to take 1000 liters of that chemical, okay, which is absolutely not necessary for most of the reactions, or for most of the experiments. Okay, we just simply need the chemicals in, suppose, ml or liter, but not, okay, 1000 liter. This much quantity chemicals we don't actually need in chemical laboratories. Okay, so that's the reason we don't use meter cube as usual. Okay, more often we simply use the smaller units of volume, ml and liter. Okay, now let's see some questions. So this question, you carefully look the way I'm trying to figure out the answer of this solution, or of this question. Okay, and then you can proceed to the next question by your own. Fine. So the question is, a balloon is filled with hydrogen at room temperature. Okay, very nice. This balloon is filled with hydrogen at room temperature. Clear. It will burst if the pressure exceeds 0.2 bar. Oh, wow, super. So if I would fill hydrogen, fill more and more hydrogen, and if the pressure exceeds 0.2 bar, balloon will burst. Okay. If at 1 bar pressure, the gas occupies 2.27 liter volume. So they are saying us that if the pressure is 1 bar, for example, okay, if I am having a container, okay, and the pressure, okay, is 1 bar, so the pressure exerted by the gas is 1 bar here. Clear? The gas occupies 2.27 liter volume. So the volume here occupied by the gas is 2.27 liters. Clear? Up to what volume can the balloon be expanded? Okay, so here the pressure exerted by the hydrogen gas, and when it is exerting this much pressure, it is occupying this much volume. Here in this question, they have not specified it very much conveniently, or very much, okay, to the point, that this pressure and volume is also at the same temperature, that is the room temperature. Okay, and they are talking about the same amount of gas. Okay, so room temperature and same amount of gas. Fine. So in questions they may not tell you this thing, but you need to like understand this thing, that whenever they are giving you some pressure and volume values, they mean that, okay, the temperature and the amount of gas is kept constant. If in the pressure they are telling you that the temperature and the amount of gas is not kept constant, then there is no point in solving that question, because we couldn't calculate the answer. Okay, we couldn't get to the answer, because what Boyle's law has taught us, that when this simple thing, PV is equals to K. So for a gas, okay, when the temperature and the amount of gas is kept constant, okay, the pressure and the volume of the gas, okay, the product of the pressure and the volume of the gas is always the same value. Okay, so if suppose the pressure is different, then the volume value, okay, would change in such a way that the product would be the same thing. So this thing we have just now studied, okay, few moments ago, and in simple terms, if I write it here as, if the gas is having P1 and V1 pressure, okay, then the product of pressure and volume is K. And if the same gas, okay, at the same temperature, and since I'm saying same gas means the amount of gas is also same, okay, if it is having P2 and V2 pressure and volume, so the product of the pressure and volume would also be the same value. Okay, fine. So at same temperature and by taking same amount of gas, the products of the pressure and the volume of that gas, okay, will always be the same value. So here also, see, they have given us some pressure, okay, and at that pressure, the volume occupied by the gas, okay. Now they are saying us that if I would fill the balloon more than 0.2, if I would fill the balloon in such a way that the pressure of the gas exceeds 0.2 bar, it would burst. Okay, and they're asking up to what volume can the balloon be expanded. So we need to expand the balloon, we need to fill the balloon, okay, with the pressure less than 0.2 bar or equal to 0.2 bar. Okay, simply not more than 0.2 bar. If I would fill the air which would exert the, if I would fill the hydrogen, which would exert the pressure greater than 0.2 bar, then the balloon would burst. So my final pressure limit inside the balloon is 0.2 bar. So I'm having P2 as 0.2 bar, and they are asking me, okay, what volume can the balloon, to what volume can the balloon be expanded, which means how much volume of hydrogen gas can be filled, okay, so that the pressure is not exceeding this 0.2 bar. Okay, so how much volume, which means how much volume, the V2, okay, because at 0.2 bar pressure, the volume occupied by the gas would be V2, and we want that our balloon should not burst. So it won't burst if we won't cross this pressure value. So we can attain this pressure value. So if we want to attain this pressure value, the volume occupied by the gas would be V2. So we need to find V2 only. Since we know that P1 V1 is equals to this constant value, P2 V2 is also equal to the same constant value. Okay, whatever be the value, 100, 200, 500, whatever be the value, but the value is same for both these products, P1 V1 as well as P2 V2. Fine. So we can simply write P1 V1 is equals to P2 V2. Correct? Okay. So now whenever you see this type of question, now I will not explain you all these things. We can just interpret that, okay, we have been given the pressure and the volume values, okay, of the same gas, same amount of gas at the same temperature. If we have been given the pressure and the volume values, okay, of the same amount of gas at the same temperature, and if they are asking any one of the value, okay, if they are asking volume or if they are asking pressure, okay, of the gas, then we need to simply use this formula. Clear? Now here P1 V1 is simply, P1 is 1 bar, V1 is 2.27 liters. Fine. P2 is 0.2 bar, 0.2 I'm just writing. V2 is, okay, we have to find it out, right? So now I'm not taking here the units as well. Simply see, if I would take 1 bar and this 0.2 bar, right? If I would write units as well, so see, the units would get cancelled. 1 bar, 0.2 bar cancelled. Remaining is just liter. Okay. Now if I were to solve this, V2 into 0.2, so I would put this 0.2 here. So 1 into 2.27 is simply 2.27 and upon 0.2. Correct? 1 into 2.27, simply 2.27 liters. Okay. And is equals to, this 0.2 is here. Okay. In the denominator. So divided by 0.2, fine, is equals to V2. Okay. Now just we can solve this simple thing and we can get the answer of the V2. So I hope you can do this simple calculation. Fine. Okay. So whatever would be the answer, that would be the volume, okay, which can be filled, volume of the hydrogen gas which can be filled in the balloon. Now it's quite simple. So see, 22.7, I can just take this point here and here point. Okay. So by shifting the point to one digit ahead, okay, it becomes 22.7 upon 2. Calculating this is 11.3, right? And then 610, so it would be 11.35. So the volume is 11.35 liters. Looking at this question, I hope you can pause here and you can try it on your own, right? So after resuming back, you can get the answer as well. Fine. So I hope you would have tried. Now let's see what the answer is. So the question is, at a particular temperature, a certain quantity of gas, okay, at this particular temperature, a certain quantity of gas occupies a volume of 74 cm cube. Okay, so some volume is given to us. Let's take it as V1, okay, which is 74 cm cube at a pressure of 760 mm Hg. So some pressure is given us. Let's take it as P1, 760 mm Hg. Fine. So they are saying at particular temperature, a certain quantity of gas. So see, the temperature is like a particular, means like constant temperature they are talking about. or they are talking about a particular temperature, fine, but here a certain quantity of gas, which means that the amount of gas is fixed. Okay, now that gas is occupying a volume of 74 cm cube at pressure of 760 mm of Hg. Fine, 760 mm of Hg. So we have taken the volume and pressure values. If the pressure is decreased to 740 mm Hg, okay, so if the pressure is decreased to 740 mm Hg, fine, of that they are talking about the same quantity of gas and at the same temperature. Fine, they haven't written it, okay, here, but see, at the same temperature they have said, and the certain quantity of gas means they are talking about the same quantity of gas only. So if the pressure is decreased to 740 mm Hg, which, okay, of the gas having same quantity, okay, if the pressure of the gas having same with the same quantity, or if the pressure of the same quantity of gas is decreased to 740 mm Hg, fine, so I have taken just P2, the another pressure value. What will be the volume of the gas at the same temperature? They are asking us volume of the gas at the same temperature. Okay, so this pressure volume values are also at the same temperature, and okay, same temperature as that of this pressure volume values. Also they are, okay, of the gas having same amount of, means also they are related, or of those gas, okay, means this pressure volume values are of that gas, okay, whose amount is also fixed. Okay, so same amount of this pressure volume values are of the same amount of gas, simply. Fine. So now again P1 V1, P2 V2, simply applying Boyle's law. Now how we are applying Boyle's law? Just we have to make sure of one thing, means in such type of questions, okay, they may give you the data that the temperature is constant, or we are talking about the same amount of gas, but sometimes they don't give, so you need to just figure it out on your, means you need to just think in this way, that you need to assume that thing, that they are talking about the same amount of, the same temperature and the same amount of gas. Okay, so applying Boyle's law, P1 V1 is equals to P2 V2, correct? So see P1 value, V1 value, P2 value, and you need to just find out the V2 value. So substituting all these values, I'm pretty sure you would get the value of V2. Okay, in the same manner we have to do just like the previous question. So this would be an homework for you. It's simple, you have to just calculate the values, right? You have to just do the simple calculation and get the answer of the volume, okay, of the gas at that same temperature. Clear? So with this we have reached the end of this video. So I hope you would have enjoyed learning with me, you would have understood the concepts, okay, but please do let me know this thing in the comment section. And as you all know, Learnohub matlab free hai par best hai. So see you then, take care, bye bye, and have a great day.